So hello guys and welcome to my channel. Today again I'm back with another important numericals on power plant design. And in this lecture we will discuss the numerical related to wind turbines. And here we have the numerical as the speed is given as a 10 meter per second. Similarly the pressure P, and that is P is equals to 1 standard atmosphere is given. Similarly, the temperature is given as here 15 degrees Celsius, and in these numericals we have to calculate the very first one is here we have to calculate the total power density. Similarly, in the second step we have to calculate the maximum attainable power density, and in the third we have to calculate reasonably attainable power density, and in the fourth we have to calculate the total power produced if turbine diameter is 20 meters. So let's see the solutions. So here the very first step we'll do here, we know the power is the formula for power is P is equals to 1 upon 2 rho into A into V cube, and power density is given as means P upon A. So P upon A equals to 1 upon 2 rho into V cube, and in order to calculate the value of rho here we have the formula as rho equals to P upon RT, and the P is given as here 1 standard atmosphere. Here we have given P as 1 standard atmosphere. So for that 1 standard atmosphere, equals to 1.01325 into 10 power 5 pascals, and the value of R will be 287. Similarly 15 degrees Celsius temperature is given, so we have to calculate that degrees Celsius into Kelvin. So for that we have to add 273. So 15 plus 273. So if you calculate these, we'll get here 1.226 kg per meter cube. And in the first step we have to calculate the power density. So power density will be right now 2 into means 1 upon 2 into means this rho 1.226, this is kg per meter cube given, and here we have the formula as power density equals 1 by 2 rho into V cube, and in place of V we have 10 meter per second, so 10 to the power cube. So we'll get here 613 watt per meter square, and the maximum attainable power density will be, and that will be almost base P max. So maximum attainable power density will be 16 upon 27, and here this 16 upon 27 is the constant value into total power density, and just now we have obtained the total power density as 613 watt per meter cube. So 16 upon 27 into 613, so we'll get here 363 watt per meter square. Similarly, in the third step we have to calculate the reasonably attainable power density. So that will be 40% of total power density, and 40% means 0.4 into total power density we have obtained in the first step, and that is 613. So we'll get here 245 watt per meter square. Now in the fourth step we have to calculate the total power density of turbine, and the turbine diameter is given as 20 meters. So for that it will be means this reasonably attainable power density into means area means pi d square upon 4, so pi into, and diameter is 20 meters, so 20 square upon 4, so we'll get here 76930 watt, and in kilowatt we'll get here 76.930 kilowatt. Similarly, here we have the next important numerical. So here we have given the two generator rated 200 megawatt and 400 megawatt operating in parallel, and the droop characteristics of the governor as given as 4% and the other is 5% respectively from no load to full load, and assuming generators are operating at 50 hours at no load, and how would a load of 600 megawatt is given be shared, and what will be the system frequency at this load, and assume free governor operations. So here the very first step we have to assume the load on first generation. So let load on the first generator equal to x, and the total load is given as 600 megawatt, and so let load on the second generator will be now 600 minus x, and we know the droop is calculated as here droop equals to minus del f upon f and upon del p upon p. So for here we have given two generators and each having the droop characteristics as 4% as 5%. So for generator 1, here we have the droop as 4%, so it will be 0.04 equals to, and minus del F upon frequency is 50. And for first generators, the first generator has the load of X, so X upon 200. And here 200 is given as here, means two generated, first one is 200 megawatt and the second one is 400 megawatt. So X upon 200, and this is for generator 1. Similarly for generator 2, the droop is 5% is given, so it will be 0.05 and equals to minus del F upon 50. And for the second load we have 600 minus X is the load given upon 400, so this is for generator 2. So from generator 1, here we can obtain the value of del F, and del F will be minus 0.04 into 50 into X upon 200, and this will be equation 1. Similarly from this generator 2, we can obtain the value of del F as del F equal to minus 0.05 into 50 into 600 minus X upon 40, and right now this is equation 2. Now if we solve these equation 1 and 2 either by dividing or by multiplying, so it will be better to divide equation 1 by equation 2, and you will get simply the value of X. So on solving, we will get the value of X as here, X is equals to 231 megawatt, and 600 minus X for second load, for second generator it is given, so 600 minus X will be 369 megawatt. So for first generator the load is 231 megawatt, and for the second it is 369 megawatt. Now we have to calculate the frequency. So here frequency will be frequency equal to F minus del F, so it will be 50 minus 0.04 into 50 into 231 upon 200, and this will be 47.69 Hertz. So in this way you can calculate such type of numericals. Thanks for watching, and please don't forget to subscribe to my channel. Thank you.